It's become pretty routine to discover new exoplanets in recent years, but every now and then, one comes along that completely changes what we thought we knew about how planets form. Today, we're going to be talking about an exciting find that's got astronomers thinking differently about how massive planets form around small stars, particularly red dwarfs. Red dwarfs, or M-type stars, are some of the most common stars in our galaxy. In fact, they make up about 70% of the stars in the Milky Way. They're cooler and much smaller than our sun, often just a fraction of its mass and brightness. You'd think these tiny stars, with their relatively low energy outputs, wouldn't be the most likely host for giant planets like Jupiter. Well, that assumption has been turned on its head thanks to an extraordinary discovery in a binary star system known as TOI-6383. TOI-6383 is about 560 light-years away from Earth. The system is made up of two red dwarf stars, which we've named TOI-6383A and TOI-6383b. The primary star, TOI-6383A, is just under half the mass of the Sun, while its companion, TOI-6383b, is even smaller, at about 20% the mass of the Sun. Red dwarf stars like these are known for their long lifespan, slowly and steadily burning for billions or even trillions of years. But what makes this system especially fascinating is the giant planet orbiting the primary star, TOI-6383ab. So, why is this such a significant discovery? The planet in question, TOI-6383ab, is roughly the same size and mass as Jupiter, the largest planet in our solar system. But here's the catch. It orbits its parent star in just 1.79 days. That means this gas giant is incredibly close to its star, much closer than Mercury is to our Sun. And we're talking about a system where the parent star itself is less than half the mass of the Sun. So how does a planet that big form around such a small, cool star? This is the big question that has astronomers scratching their heads. The usual way we think about how planets form suggests that red dwarf stars, which usually have less massive disks of material around them, don't have enough material to form giant planets. Previously, it was thought that gas giants like Jupiter were more likely to form around stars similar to or larger than our Sun. But TOI-6383ab shows that this isn't necessarily the case. If a star as small as TOI-6383a can host such a massive planet, it suggests there's more to planetary formation than we previously understood. There are two main models that explain how planets form around stars. The first is the core accretion model. This theory suggests that planets start off as small dust particles in a disk of gas and dust that surrounds a young star. As time goes by, these particles stick together and grow larger, eventually forming planetesimals, basically baby planets. Once these planetesimals reach a certain size, they start to attract more material due to their gravitational pull, growing into full-fledged planets. For gas giants like Jupiter, the core must grow large enough to capture a significant amount of gas before the disk dissipates. There's one issue with applying this model to red dwarf stars, though. Their protoplanetary disks are much smaller and less massive than those surrounding stars like our Sun. This means there might not be enough material in the disk to form a giant planet through core accretion alone, especially given the time frame needed before the gas in the disk is blown away by stellar winds. So how could a planet as massive as TOI-6383ab form around a star that is less than half the mass of the Sun? This brings us to the second theory, which is disk instability. This is where a massive protoplanetary disk can become gravitationally unstable, causing parts of the disk to collapse and form giant planets directly. This process can happen much more quickly than core accretion and doesn't require the formation of a massive core. Instead, planets form directly from the disk material itself. Disk instability is one of the theories being explored to explain how massive planets can form around small stars like red dwarfs. The discovery of TOI-6383ab lends further support to the idea that disk instability could play a significant role in the formation of gas giants around red dwarf stars. Even with this theory, there are still lots of questions left unanswered. For instance, how common is this process? And why have we only found about 20 massive planets around red dwarf stars so far? The GEMS survey, which discovered TOI-6383ab, is working to answer some of these questions. GEMS, which stands for searching for giant exoplanets around M-dwarf stars, is dedicated to finding more giant planets orbiting red dwarfs. As we discover more and more planets around these small, cool stars, we'll get a better understanding of how they were formed. TOI 6383. AB is more than just a one-off. It could be the key to a new understanding of how planets are formed. And it's not just about the larger planets. Red dwarfs are also known for having a variety of rocky planets, including many that fall into the super-Earth category. These planets, which are several times the mass of Earth, are thought to be pretty common around red dwarfs. This raises questions about what conditions might make some red dwarf systems more favorable for planet formation than others. It's interesting to note that red dwarf stars have been a major focus in the search for potentially habitable exoplanets. As these stars are cooler and less luminous than the Sun, their habitable zones, the region around the star where conditions might be right for liquid water, are much closer to the star. This makes it easier to spot planets in the habitable zones of red dwarfs, using methods like transit photometry, which involves looking for periodic dips in a star's brightness caused by planets passing in front of it. The GEM survey uses NASA's Transiting Exoplanet Survey Satellite, TSS, to detect these transits and follow-up observations with ground-based telescopes to confirm the existence of planets and measure their properties. By using a combination of transit photometry and radial velocity measurements, astronomers were able to confirm the mass and size of TOI 6383ab. Radial velocity is a way of measuring the slight wobble of a star, caused by the gravitational pull of an orbiting planet. By combining these two techniques, scientists can get a pretty accurate estimate of the planet's characteristics, including its mass, size, and orbital period. The discovery of TOI 6383ab not only adds to the growing list of known exoplanets, but also offers valuable insights into how planets form in binary star systems. Binary systems, where two stars orbit each other, are pretty common in our galaxy. However, it can be tricky to find planets in these systems because the gravitational interactions between the two stars can disrupt the formation of planets or make their orbits unstable. In the case of TOI 6383, we're looking at a relatively stable binary system where the planet orbits one star, while the other star remains a distant companion. This raises even more questions about how the presence of a second star might influence the formation and evolution of planets in such systems. Another fascinating aspect of this discovery is the potential for future observations. TOI-6383AB could be a great candidate for more detailed studies with next-generation telescopes like the James Webb Space Telescope, JWST, or the Extremely Large Telescope, ELT. These powerful instruments will let astronomers study exoplanet atmospheres in more detail, looking for signs of chemical compounds like water vapor, methane, and even potential biosignatures, molecules that could indicate the presence of life. While it's unlikely that TOI 6383ab will have life on it, given how close it is to its star and that it's a gas giant, studying its atmosphere could reveal important clues about how gas giants around red dwarfs are formed and composed. And who knows, as we continue to discover more planets around these small, cool stars, we might just find one that's perfectly habitable. Right, what's next? The GEM survey is going to keep on looking for more giant planets around red dwarfs. The plan is to expand our inventory from 20 massive planets to at least 40. This larger sample size will let astronomers test competing models of planetary formation more rigorously, helping us understand whether core accretion or disk instability is the dominant mechanism for forming giant planets around small stars. In the meantime, discoveries like TOI 6383ab show us that the universe is full of surprises. Every new exoplanet offers a chance to learn something new about the amazing variety of planetary systems in our galaxy. As our tech gets better and our methods get more sophisticated, who knows what we'll find next? One thing's for sure. The discovery of TOI 6383ab has opened up a new chapter in the study of planetary formation, and it's only the beginning.